The definition of conditional expectation is the same as the definition of ordinary expectation, except that now we use the conditional density or mass function. In other words, if x and y are random variables with a joint PMF or PDF given by f sub xy, then the conditional PMF or PDF of x given that capital Y is equal to little y is given as follows. And we use this conditional density function in our definition. In other words, if x and y are discrete, then we define the conditional expectation of g of x given that capital Y is equal to little y to be the sum over all possible values of x of the function g of xi multiplied by the conditional density function. And in the same way, if x and y are continuous, we have the same definition except that now we use an integral. Observe that the expectation of g of x given that capital Y is equal to little y is simply a number. But we can also define a random variable, the conditional expectation of g of x given y, as follows. Suppose that x, y are random variables on a sample space omega and that g is a real function. Define the random variable, the expected value of g of x given y on omega as follows. If little omega is an outcome, a state of the world, then the conditional expectation of g of x given y is a random variable whose value in that state of the world is simply the conditional expectation of g of x given that capital Y is equal to little y, where here little y is the value of capital Y in that state of the world. Thus, to compute the value of the conditional expectation in the state of omega, you have to do two things. First, you must compute the value of capital Y in that state, and let little y be the value of capital Y. Then compute the conditional expectation of g of x given that capital Y is equal to little y. In other words, if x and y are continuous random variables, that would be given by this integral, as shown on the previous slide. And this number is the value of the conditional expectation in that state of the world. Observe, therefore, that the conditional expectation of g of x given y is a function of y. In other words, if you know the value of capital Y, then you can compute the value of the conditional expectation. Here are some basic properties of conditional expectation that are very useful for computation. Firstly, the conditional expectation of g of x given y is a random variable, and we can ask what is the expectation of this conditional expectation. And the answer is that it is just the ordinary expectation. In other words, if you first condition on y and then take the expectation of the resulting random variable, you just get the ordinary expectation. This is called the law of iterated expectations, also known as the Tower property. Let's see why. The conditional expectation is just a function of y, and hence its expectation is computed in the usual way as a sum over all the possible values of y of the value of the conditional expectation times the probability. Now, the conditional expectation is the inner integral here. Now here we integrate first over x and then over y, but we will now interchange the order of integration and integrate over y first and then over x. When we do that, we can take that g of x outside, and we just obtain the following integral on the inside. Now, by definition, this product is just the joint density function of x and y, and hence its integral is just the marginal density function of x. So we end up with the sum over all possible values of x of the value of g times the density function of x, which is by definition the expectation of g of x. In the case where x and y are discrete random variables, the argument is the same, except that the integral is replaced by a sum. The second property is the following. If g and h are functions, then the conditional expectation of g of x times h of y given y is just the conditional expectation of g of x given y times h of y. The intuition here is as follows. The conditional expectation of g of x given y is the best estimate of the value of g of x given that we know the value of y. So the conditional expectation of g of x times h of y given y is the best estimate of g of x times h of y given that we know y. But if we know y, we know h of y, so we don't have to estimate it. Hence, we only have to estimate g of x, i.e. the best estimate of g of x times h of y given y is the best estimate of g of x times h of y. We leave the formal proof of this fact as an easy exercise. Let's now consider the relationship between expectations and independence. We have already given an example that, in general, it is not the case that the expectation of a product is the product of the expectations. However, if x and y are independent random variables, then this is the case. In other words, if x is independent of y, then the expectation of the product x times y is just the product of the expectation of x with the expectation of y. The proof is straightforward. Here assume that x and y are continuous random variables with a joint density function f(x) sub y. Since x and y are independent, the joint density splits up into a product of the marginal densities. Thus, by definition, the expectation of x times y is just the double integral of xy times the joint density function. And because the joint density function splits into the product of the marginals, we obtain the following. Now the inner integral here is just the expected value of x, which is a constant, and so we can take that outside the outer integral. The outer integral then is just the expected value of y, and the result follows. Here's another result that is intuitively obvious. If x and y are independent, then the conditional expectation of g of x given y is just the expectation of g of x. Recall that intuitively speaking, if x and y are independent, then knowledge of the value of y does not cause us to revise our estimate of the value of x. And hence knowledge of the random variable y does not cause us to revise our estimation of the expectation of g of x. Thus the expected value of g of x given y is just the expected value that we would have had if we had no information about y. And this is because y tells us nothing new about x. The proof is straightforward. If x and y are independent continuous random variables, then the joint density function splits into the product of the marginals, and hence the conditional density function is just the marginal density function. Hence, for every value little y of capital Y, we have that the conditional expectation of g of x given that capital Y is equal to little y, by definition, is this integral over here, but the conditional density function is just the marginal density function, and this integral by definition is the expectation of g of x. Another result that is intuitively true but harder to prove is the following. If x and y are independent and g of x and h of x are real functions, then g of x is independent of h of y. For suppose that g of x and h of y are not independent. Then knowledge of y is knowledge of h of y. But since h of y and g of x are not independent, knowledge of h of y will tell us something about the value of g of x. And of course, knowing something about g of x tells us something about the value of x. Hence, knowledge of y tells us something about the value of x, in which case x and y are not independent. Hence, if x and y are independent, then so are g of x and h of y.